All right, so let's get started. Today is 1.5, Parent Functions and Transformations, and this is day 1. A parent function is the simplest of the functions in a family. This is the function that is transformed to create other members in the family of functions. Below are some common parent functions, which you will see frequently in this chapter and beyond. You must memorize the shapes and be familiar with specific points for each of these. So I'll highlight the specific points that you need to know, but once again, you need to know the shapes. Like you need to know that a parabola, x squared, is u-shaped, and absolute value is v-shaped, and things like that. Okay, so we're going to start with a constant function. So here's your constant function, f of x equals c. Now where c is any real number, so f of x equals 2, f of x equals -6, f of x equals 5, f of x equals -0.5. Those are all constant functions. So when I go to plug in -2 for x into this equation, think about this. When I went to go to plug in -2 here for x, -2 quantity squared is 4. But when I go to plug in -2 for x in my first equation, there is no x. So you get an automatic output of c, whatever that number is. So like if it was a 2 there, then it'd be all 2's. All right, now I'm going to graph those points. So left 2 up an amount. So I'll say this much. I don't know how much it is because I'm just making up the value of c. Left 1 up that same amount. Left 0 up that same amount. So on and so forth, right? So if you start making all of the points there, you're going to get a line. You're going to get a horizontal line. If you look at the domain of that line, it goes from an arrow to an arrow, so all real numbers. And then your range is whatever that y value is. So in our case, we just made it up. So it's just c in brackets because those are the values. All right, next, a linear function. When I plug in -2, I get -2, -1, -1, 0, 0, 1, 1, 2, 2. Graph those points. Now connect all of those points to form your sloped line. Domain, arrow to an arrow, all real numbers. Range, arrow to an arrow, all real numbers. Next is the quadratic function. So I have f of x equals x squared. When I plug in -2, I get 4. -1, I get 1. 0, I get 0. 1, I get 1. 2, I get 4. So let's graph this quadratic function, which looks like a parabola. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. You can connect those and you can see that it's U-shaped. The important points that you need to know, the specific points, these 3 points right here is what you're going to transform. So you have to know that the parent always has points at 0, 0, 1, 1, and -1, 1. And then if I want to move this graph right 6 and down 2, I'm just going to move those 3 points right 6 and down 2. And then I can graph my parabola. The domain, arrow to an arrow, -infinity to positive infinity. My range, the lowest my values go, are 0, and then to infinity. All right, next, the cubic function. The cubic function is y equals, or f of x equals, x cubed. That's the parent function. So let's plug in some values to see what this shape looks like. -2 cubed is -2 times -2 times -2, which is -8. -1 times -1 times -1, 0 times 0 times 0, 1 times 1 times 1, 2 times 2 times 2. All right, so let's graph these points. -2, 8, sorry, -2, -8. That falls off the graph a little bit, but that's okay. Okay, the right-hand side, as you can see, looks like an upward-facing parabola, part of it. And then the left-hand side looks like part of a downward-facing parabola. Once again, the important points here are -1, -1, 0, 0, and 1, 1. You're going to transform those 3 points and then know that this is what the graph looks like. The right side looks like an upward-facing parabola. The left side looks like a downward-facing parabola. It goes from an arrow to an arrow, so domain's all real numbers, and so is your range. Next is the square root function. So I have the square root of plugging in 0, I get 0. Plugging in 1, I get 1. Plugging in 4, I get 2. Notice I didn't ask you for the square root of 2 and the square root of 3 because those are decimals and I want you to plug in points that we know the answers to. Also, I didn't have you plug in negative x values because if I put in a negative x value, I get an imaginary output. This graph paper is for x, y coordinate points, not imaginaries. 0, 0, 1, 1, 4, 2. And those are your 3 specific points that we're going to want to know and transform. Domain, 0 to infinity. Remember why this is because we're not going to be able to plug in negative numbers into this parent function. And your range is also 0 to infinity because we're never going to get a negative answer when we take the square root of something. Okay. Next, f of x equals the absolute value of x. So let's see what absolute value function looks like. Plug in negative 3, you get 3. Negative 2, you get 2. Negative 1, you get 1. 0, you get 0. 1, you get 1. 2, you get 2. 3, you get 3. So now you can graph those points. And you can see that an absolute value function is V-shaped. Critical points, the important specific points that you should move, the same ones that you would use for a parabola. But remember, a parabola is U-shaped and absolute value is V-shaped. It also has the same domain, negative infinity to positive infinity, and the same range, 0 to infinity. The last function that you have to know the shape of is the reciprocal function. So before I move on with this table, the first thing I'm going to talk about is plugging in 0. If I ask you to plug in 0, you're going to get that the function's undefined there. So at x equals 0, this function is undefined. So if it is undefined there, you are going to have nothing there, meaning a vertical line. Or sorry, nothing there, which is an asymptote, is a vertical line, not an actual vertical line. All right, now if you look at the function again and I say, okay, what can I do to make this be 0? 1 divided by what is 0? You can't do it because in order for a fraction to be equal to 0, the numerator has to be 0, and this isn't. So y will also never be 0. So we have a horizontal asymptote right there. So this is the starts of what a reciprocal function looks like. It has a vertical and horizontal asymptote, and if there's no translations moving it right or left, up or down, this is where the asymptotes will stay. All right, so now let's see when we plug in negative 2. When we plug in negative 2, we get negative 1/2. When we plug in negative 1, we get negative 1. When we plug in negative 1/2, negative 2, positive 2, positive 1, and 1/2. All right, now let's graph these points. I'm going to switch colors here just so the points don't accidentally blend into the asymptotes. Oops. Negative 2, negative 1/2. Negative 1, negative 1. And negative 1/2, negative 2. So now you can see what this, it's called a branch of your reciprocal function looks like. Now we have this branch, over a half up 2, 1, 1, over 2, up a half. And you can see this other branch right here. So notice I'm getting closer and closer and closer to the asymptotes. People accidentally go like this. Okay? That's not what asymptotes are there for. They're there so you can get closer and closer and closer to them, never crossing, never touching. All right, if you look at your domain, it goes from an arrow to an arrow, but there are no x values at 0. So you're going to say from negative infinity to 0, union 0 to infinity. Same thing goes for your range, negative infinity to 0, union 0 to infinity. Okay, so these are the parent functions that you have to have memorized. I forgot to mention the specific points on this graph that you should know. They're not actually points, the asymptotes. You need to know where your asymptotes are, and then also that there's a point up one right one from the asymptote, and down one left one from the asymptote. Okay. So the first type of transformation that we are going to talk about is a translation. Now, in integrated, you called these translations, vertical and horizontal translations, and you would just say up 6, left 2, right 5, down 7. We are going to use this specific vocabulary word, vertical translation. It has to be there. Now, followed by, you would say up something or down something, but you have to say vertical translation. Same idea. We're going to say if the graph is moving right or left, we're going to call it a horizontal translation. And then we're going to say left how many it's moving or right how many it's moving. Now, how do we characterize these? The function will have a vertical translation if, let's call the function g of x with the translation that is. It has the parent function, and then on the parent function, either something's being added or subtracted off. I'm going to put plus k for now. This is going to move the graph up or down. If it was plus 3, the graph would move up 3. If it was minus 3, the graph would move down 3. But once again, this is on the outside of the parent. Please consider f of x the parent. Okay. Right or left, you would have g of x, once again we'll call it, equals. And then this would be f of x minus h. Okay, so notice this is inside the parent. So if you have something directly affecting x, that's going to move your graph left or right. So this moves the graph left or right. Now, you might recall from Integrated and Algebra 2 that if you saw x minus 5 in parentheses, that would move the graph right 5. X plus 5 in parentheses would move the graph left 5. All right, we're going to graph each function and describe the transformation. So the first one is f of x equals the absolute value of x. Once again, we need to know these 3 points and then that it's V-shaped. My line's a little crooked here. Let's try that again. There we go. Left side. Okay, so we're going to graph each function and describe the transformation like we said here. So first off, notice that this is inside the parent. Since it's inside the parent, it's going to move it left or right. Since it's a plus one, that's moving it left 1. So we are going to describe this as a horizontal translation. Left 1. Now let's move the graph left 1. You're going to move your 3 specific points here, your 3 critical points here. And now the graph is moved left 1. All right, this one right here, I have the minus 1 on the outside of my parent. On the outside, that's a vertical translation. So I have a vertical translation down 1. So once again, I'm going to take those 3 points, 1, 2, 3. It's V-shaped because it's absolute value, and that's what it looks like. All right, go ahead and pause the video and try the next one on your own. All right, for this, you're going to say 2 things. So remember, to get full credit here, you would have to say there's a horizontal translation, right 2. And there's a vertical translation, up 3. So those 3 points, that the first one being at 0, 0, it's now going to move right 2 and up 3. So right 2, up 3. And then I have those other 2 points. And there's my absolute value function. Okay, that's it for today. Go ahead and get started on the homework.